This is the fourth video on partial fractions decomposition. The integrals on this video actually are not integrals where we use partial fractions decomposition, but what we've talked about in previous videos is that you can end up with irreducible quadratics in the bottom. And as part of the expansion, you can get a fraction like what you're seeing on the screen. This is how you would do the integral of that. And so real quick, what I mean is you might have a partial fractions decomposition where you have something in the numerator over, say, x plus 3 times 9x squared plus 16 dx. And so you do the partial fractions decomposition where you get a over x plus 3 plus bx plus c over 9x squared plus 16, and you do all the work and you get whatever a is, it wouldn't matter, and here b would be 5 and c would be -2, and you work out the problem, and when you split it up you get this integral for the bx plus c over 9x squared plus 16 part. So these could result from a bigger problem. We're going to focus on how to do the integral itself. Okay, so this first version is one that we talked about in u-substitution. And so technically this is just a u-substitution problem. But what we do is we split it into two integrals. So if the numerator was just 5x, we would want to use log because the derivative of the bottom is 18x. If the numerator was just 2, we would want to use inverse tangent because if we factor the 16 out, we can get that to match the form we want. So on the problem on the left, in blue, we write u equals 9x squared plus 16. du then is 18x dx. So we're going to pull the 5 out. We're going to keep this as 1 over 9x squared plus 16, and we put the x next to the dx. I need an 18 inside, so I multiply outside by 1 over 18, and now we deal with the second integral. On that problem, I pull the 2 out, but I also factor a 16 out of the denominator, and I get 1 over 1 plus 9/16 x squared dx. So over here, we're going to choose a different variable, v, and v is going to be 3/4 x. And I don't mean v as in like integration by parts, but we're just using a different letter because we already used the letter v, or we already used the letter u. So dv is 3/4 dx. And so on the second integral, now we're going to multiply inside by 3/4 and outside by 4/3. So let's write some more on this problem. So we get 5/18, integral 1 over u du, minus now 1/8 because 2/16 reduces, multiply outside by 4/3 and inside by 3/4. The 3/4 dx is the du, but when we square v, we get the 9/16 x squared. That's why we chose v the way we did. And so we get 1 over 1 plus v squared dv. The 1/6 comes from multiplying those two fractions together. That gets us 5/18 natural log of the absolute value of u minus 1/6 inverse tangent of v plus c. That gets us 5/18 natural log of 9x squared plus c. Plus 16. And then minus 1/6 inverse tangent of 3x over 4 plus c. Okay, so that's a quick review of what we did when we did u-substitution. What we want to talk about now is if there's a middle term in the quadratic, the irreducible quadratic. So instead of 9x squared plus 16, maybe it's 9x squared plus 2x plus 16 or something along those lines. Real quick, I want to review a technique called completing the square because we use that when we're doing the irreducible quadratics that have a middle term. And so it should be familiar from algebra that if I have x minus 3 squared, we should at this stage in math be able to figure out that's x squared minus 3x plus 9 without writing out the multiplication. And if you're not clear on that, that would be something worth meeting with me about. But x minus 3 squared is x squared minus 6x plus 9. X plus 7 squared is x squared plus 14x plus 9, or plus 49. And the idea is the first term is the first one squared, so the x squared. The last term is 7 squared, or 3 squared on those two. And the middle term is the two terms inside the parentheses. So like on the first one, x times negative 3 is negative 3x, but then doubled because you get it twice when you distribute that. So you get negative 3x times 2, which is negative 6x. On the second one, you get 7x times 2, which is 14x. And so the idea with completing the square is that if you had these two terms, so if I knew that I started an expression with x squared plus 10x, the idea is what perfect square like the ones on the left does that come from? And that comes from x plus 5 squared. And so what we'd like to be able to do is manipulate x squared plus 10x to get an expression that has x plus 5 squared in it. And the way we can do that is x squared plus 10x is not x plus 5 squared, but x squared plus 10x plus 25 is. So if I add 25 and subtract 25, now this part is equal to x plus 5 squared, and the whole thing is equal to x plus 5 squared minus 25. Let's do that one more time real quick, and then we'll see that in the example we're about to do. So if I have x squared, say, plus, we'll do minus this time, x squared minus 12x, and we'll say this time plus 100, then that's not a perfect square as written, but x squared minus 12x is the beginning of x minus 6 squared. And so the goal of completing the square is to kind of get that type of thing to show up. So a perfect square of a binomial to show up. Well, x minus 6 squared is not the same as what's written above there, but it is the same as x squared minus 12x plus 36. And now the first two lines are not equal to each other, but if I also subtract 36, now those first two lines are the same as each other. The second line is not equal to the third line, but if I combine those, so the x squared minus 12x plus 36, that's x minus 6 squared. 100 minus 36 is 64. And now this last line is actually equal to the top line. And so we'll use that technique late in the next problem. But real quick, remember that when we had an irreducible quadratic here in the bottom, this split into a log and an inverse tangent problem. We're going to do the same thing for the next problem, but the algebra is a lot more involved. So on this problem, we have an irreducible quadratic on the bottom. We know that because b squared minus 4ac is 36 minus 4 times 1 times 100, times 25, which is 100. And so then 36 minus 100 is negative 64. And so because that's negative, we know this is an irreducible quadratic. So we're going to force log and inverse tangent to work. If log is going to work, then u would equal x squared plus 6x plus 25, and du would be 2x plus 6. That's not very close to the numerator, but it's at least in the same form. So we get to 2x plus 6 in a couple of steps. The first thing is we factor the 3 out and get x minus 5/3. And now I need 2x there. So I multiply inside by 2 and outside by 1/2. Let's do this underneath. So we'll do 3 times 1/2 but now the 2 distributes to the top. Now, I've got the 2x that I want, but I also need 2x plus 6. The most obvious way to try to get plus 6 would be to factor out 10/3 or to multiply that by something to get it to be 6. The problem with that is that'll mess up the 2 that we already got. So what we're going to do instead is we're going to put in plus 6. And so I'm going to write this for now and to look closely, but I've spaced out the top a little weird, but this integral is actually the same exactly as the integral above it. But what we're going to do is we're going to add in plus 6 here. And if we do that, we also have to subtract 6. The reason we do that is because now we can split this into 2 integrals and get 3/2 integral 2x plus 6 over the bottom. We do that because that's the form that we want for natural log. And then on the second one, we have 3/2, and then negative 10/3 minus 6 is negative 10/3 minus 18/3, which is negative 28/3. And then we have 1 over x squared minus 6x plus 25. Now, the first integral matches log because it's 1 over u du. The second integral is a lot like the integral we started with. The difference is the top is degree 0, so it's a constant over an irreducible quadratic. And man, please don't randomly change 6's from positive 6 to negative 6. All the way through here, we're going to go with x squared plus 6x plus 25, which doesn't affect anything to this point, but would affect something later. So just please fix that, and I apologize for the mistake. But okay, so what we're going to do is we're going to go ahead and write this first one as 3/2 integral 1 over u du. And then we're going to simplify this to minus 14 integral 1 over x squared plus 6x plus 25. We're going to try to force the second one to match inverse tangent. The biggest difference between this and the inverse tangent form is that the inverse tangent form has 1 over 1 plus u squared du. And so there is an irreducible quadratic there, but there's no middle term. So we're going to do completing the square to kind of force it to match that form. So we come up on the side and do completing the square. So x squared plus 6x is the beginning of x plus 3 squared. X plus 3 squared is x squared plus 6x plus 9. So to make the first 2 lines equal to each other, we add 9 and subtract 9. Now we fill in plus 16, and the last line is equal to the first 2 lines. So what that means is we can rewrite the last integral as 1 over 16 plus x plus 3 squared. Now let's make that a little bit neater. Now it's a lot closer to inverse tangent, but we need to get rid of the 16. All right, so this is scratch work on the side, and we're going to continue with this work down here. So we've got 3/2 integral 1 over u du. We're going to factor out 16, so we get 14 over 16. Forgot the dx. 1 over 1 plus 1/16 x plus 3 squared. That now is the inverse tangent form if we let v equal the square root of the second term. So v is 1/4 times x plus 3. The derivative of that is 1/4, so dv is 1/4 dx. So we multiply inside by 1/4 and outside by 4. And then the 7/8 is just reducing the 14 over 16. So we get 3/2 integral 1 over u du. minus the 4 and the 8 cancel, so 7/2 integral 1 over 1 plus v squared dv. The integral of 1 over u du is natural log absolute value of u. The integral of 1 over 1 plus v squared is inverse tangent of v. And so now we plug in u, and if we scroll back up, u was originally x squared plus 6x plus 25. We could actually drop the absolute value here because it ends up that that's always positive, but that's not necessary. And then 7/2 inverse tangent of v, but v was x plus 3 over 4 plus c. As you can see, this is quite an involved problem. It is one that you need to practice. So if you look at the first partial fractions worksheet, number 4 on the first partial fractions worksheet is like this. I hope it's not the exact same problem, but I think it's very similar. And then you'll see, I think, a couple on the second partial fractions worksheet and probably some on some old exams. This is how you handle, if you have an irreducible quadratic in the denominator, this could, in theory, come out of a larger partial fractions problem. All right, that's it for this video. If you have questions, just let me know. Thank you for watching.